So what we're looking for is how the stars end up changing as we move our gravitational lens about the sky. So you can see that as we go past stars, they end up distorting into arcs due to our gravitational lens. And if I end up rotating things around so I can see what I'm doing a bit better. Oops. I think I've just lost my, this video camera seems to be quite touchy. So let's see. Yep, we're back again. Right. So, when I'm back in, yep. Right. So if we end up getting complete alignment, you can see how we get a black ring all the way around the stem of the wine glass. And that's when we're in perfect alignment. But if we're slightly off alignment, we can see that the star ends up being an arc instead. And then further away, it comes back to being a star and just shifts its position a bit. And the interesting thing is that the arc, the radius of the arc always points towards the center of the wine stem, towards the center of the gravitational field that's causing the lensing. So you can see as we change the alignment, what different effects we end up getting. So, yep, now you fully understand everything there is to know about gravitational lensing. So I think then we can start our talk and start using it. Right, okay, I shall switch back to the other camera. Right, okay, so the talk is about dark matter. The first thing I thought I would end up commenting on is that I'm not going to cover dark energy at all. Dark energy and dark matter are completely different things with completely different explanations. And whereas with dark energy, we know almost nothing, dark matter, the situation is a little better, as you'll find out. We have quite a lot of information on dark matter. So we're told that 85% of the mass of the universe is this dark matter that we can't see, and only 15% is down to the ordinary matter of atoms and molecules, people, stars, and planets. Despite not being able to see dark matter, we've got quite a lot of compelling evidence to say that it really does exist. So the questions I want to answer during this talk are, where is this dark matter? Is it evenly spread across the universe, or is it in some places and not others? What evidence do we actually have that it really genuinely exists? Or perhaps maybe it doesn't exist, but we just need to modify the rules of gravity. If we decide it does exist, what is it made of? Is it made up of macho or WIMPs? Is it hot, warm, or cold? So we're going to try and understand the terminology that's been added to this field. And then finally, we need to answer a very urgent question, and that's if we're trying to lose all that weight that we've put on during lockdown, we might want to know if it's reasonable to complain, I'm trying to lose the weight, but dark matter is so hard to shift. So by the end of the talk, you should have a good idea whether that's a reasonable excuse or not. The slide here is the Earthrise over the moon from Apollo 8, and I included it because where dark matter is quite an intriguing question. Is the Earth 85% dark matter? Do we need to include dark matter when we send a space probe out into the solar system? So Here's our first graph of the talk. I'm not sure I'm allowed to display graphs, but hopefully this one is fairly intuitive to understand. And it's the orbital velocities of the planets around the Sun. So for instance, we can see Mercury in the top left there. And that tells us that Mercury is very, very close to the Sun. And because it's in that intense gravitational field, it has to orbit very fast in order to counteract the force of gravity. On the other hand, when we look at the outer planets like Neptune, we see that that's now at 30 astronomical units from the Sun. It's in a much, much weaker gravitational field, so it only needs to orbit very, very slowly in order to counteract gravity. So we can plot the curve that the formula predicts. And this formula is based on all of the weight of the solar system being inside the Sun. And that's a reasonable assumption because 99.8% of the solar system's mass is the Sun. 99.8. So providing there's no significant dark matter in our solar system, the planet should lie exactly on this curve. But I want to now delve into a little bit of a thought experiment. What if, when we observed Jupiter's orbital velocity, it was exactly the same as the Earth, despite its bigger distance? And there's only two ways we'd be able to explain that observation. One would be our theory of gravity was completely wrong. The alternative is we had some invisible material in either a ring or a shell in between the Earth and Jupiter's orbit. And that extra mass would then increase the gravitational field at Jupiter, and then its orbital velocity would have to be faster, and it could then equal the Earth's. And indeed, the orbital velocity, what that tells us is the total amount of mass within its orbit. It doesn't need to be at the center, it can be anywhere, but it does tell you the total amount of mass. So you can increase the orbital speed by putting mass, significant mass, anywhere within its orbit. It turns out that the planets are exactly on this curve as far as we can measure. So dark matter has a negligible effect on the orbits of the planets in the solar system. Here, normal matter absolutely dominates. We have no observational evidence of dark matter here at all. And indeed, when we sent the Voyager probes out into the solar system, we didn't have to include dark matter at all when we calculated their trajectory. And now in 2020, we still, they're exactly where they ought to be, based on Einstein's general theory of relativity, which of course is the real theory of gravity. It's precisely where it should be, just based on the Sun's normal mass. So it would appear in the solar system, yeah, dark matter is negligible. So to find any evidence of dark matter, we have to move to galactic scales. So here's, we have a cartoon of our galaxy. And we can see that the galaxy has a stellar bulge in the center. Let's see if I can get a pointer on as well. Here we go. Hopefully people can see the pointer I've got. So we've got a stellar bulge, which has a large amount of mass in it. We then have the stellar disk, where the spiral arms reside. And the disk has a lot of mass in it as well. The stellar disk is embedded in a bigger gas disk, which is both thicker than the stellar disk, and it also extends to much greater distances from the bulge. We also have a halo around the galaxy, which is a roughly spherical halo, and that's where the majority of the globular clusters we observe are. So globular clusters are very compact spherical clusters of stars that are very ancient. They're probably as old as the galaxy is, and they're traveling in orbits that take them high above the plane of the galaxy. We also have a lot of metal poor stars in this halo as well. The density of these stars is much lower than in the disk, but there's probably more of these stars than there are more of these single stars than there are stars in the globular clusters. So this halo population, they don't have well-behaved orbits like the disk stars do. The disk stars have a very circular orbit around the galaxy, whereas the halo objects, their orbits are very, very random. They might be going backwards or forwards and at any orientation. So for the visible mass, we have a concentration in the bulge. Next, we have the mass in the gas and the stellar disk in the spiral arms of the galaxy, and then the galaxy's halo has a fairly negligible amount of mass in comparison. We now come to the heroine of our story, which is a young woman called Vera Rubin. She became interested in astronomy at the age of 10 when she was observing stars from her bedroom window, and had a very strong interest in it ever since. Despite her strong interest, her school teachers advised her to avoid science and that she really ought to become an artist instead. Fortunately, she didn't, and she ended up doing an astronomy degree in 1948 at Vassar College. She got a good degree and then applied to Princeton to do a master's, and she was rejected. She was rejected because she was female. It was another 27 years before this shocking policy was changed. So instead, she ended up doing a master's at Cornell University. One of the many things she ended up doing was measuring the orbital speed of stars in the Andromeda galaxy. She had heard earlier reports of missing matter in galaxy clusters, so she wanted to find out if that was really true, and to find a way of measuring it precisely. And she realized that spectroscopically measuring the speed of stars in the Andromeda galaxy should do the trick. So by seeing whether stars were redshifted or blue-shifted, she could measure their orbital speed, and by doing that at different distances from the galaxy center, she could create a rotational orbital rotational curve for the galaxy. And when she did this, instead of finding a curve that rapidly diminished to low values with increasing distance, instead it showed a very flat curve where the rotational speed stayed constant through the whole of the disk. This required about 5 to 10 times the amount of matter that we could actually see in the form of stars. So she had proven beyond any doubt that either dark matter existed or our understanding of gravity was wrong. And this concept of dark matter ended up completely revolutionizing our ideas about cosmology. So many scientists feel that she really should have been awarded the Nobel Prize. Of course, she wasn't, but she never commented on this herself. So now I want to show a little movie of the galaxy rotation. That's not what I wanted to do. Let's try that again. So on the left, we have a theoretical model of a galaxy without any dark matter, and the galaxy on our right is one with 85% dark matter. And we can see that the curves that we have, they're lined up with the distance of the galaxy. So the origin of the axis there corresponds to the center of the galaxy, and then the edge of the visible disk corresponds. Hopefully you can see my pointer. So what I want you to look at is not the spiral arms, but the dots within the galaxy. So we can see when we play it on the left that the stars at the center are whipping around, but the H2 regions are on the spiral arms. As we get towards the edge of the galaxy, they're moving really, really quite slowly. And that's exactly what we'd expect with a weaker gravitational field towards the edge of the galaxy. And now if we look on the one on the right, we can see that the H2 regions, those red dots at the edge, are moving a lot faster than the galaxy on the than our simulation on the left. Once you get away from the center of the galaxy, the rotation stays fairly constant with distance, and that requires the 85% dark matter, and it also means that the dark matter must be distributed so that it's not all at the center. There's lots of it in between the center and the edge of the galaxy, just like we needed to add a shell of material to make Jupiter orbit the same speed as Mars. So this is the modern observations of galaxies' orbital rotation curve. And this is for, you've probably recognized the galaxy M33, the Triangulum galaxy. And again, the axis is arranged so that the origin is at the center of the galaxy. And then we have the edge of the visible disk at around about 15,000 light years. And we have the edge of the gas disk at around about 50,000 light years. So we can see the yellow data points are from observing the orbital speed of the stars. And when we get to the edge of the optical stellar disk, we then have to switch to measuring the rotation of the gas disk, which we can do with radio telescopes, looking at the 21 centimeter emission line from hydrogen molecules. And we can see that the rotational curve just keeps on going. The speeds are getting faster and faster, despite the increased distance from M33, indicating there's a lot of dark matter that extends way beyond the visible disk. The dashed line underneath is showing you what the curve would be if there was no dark matter. It's a little bit different from the curve that we got from our solar system, but that's because the solar system, all the mass is centered in the sun, whereas in a galaxy, the mass, even if dark matter didn't exist, the matter would be more evenly spread. So you get a curve that doesn't go down quite as rapidly. But there's still a huge divergence between what we'd expect from the luminous matter and what we actually observe. So this is looking at the observations in a bit of a more of a where the contributions come to produce these different orbital velocities. So the solid red line is what the best fit line to the observations we've actually got from M33. Then the dotted line, this one's the contribution made by the dark matter. The small dashed line is the contribution from the stars, and the long dashed line is the contribution from the gas disk. So we can see close to the nucleus of the galaxy, stars are quite significant in their importance. As we go further out, it's the dark matter that becomes very dominant. So we've been able to track the dark matter as far as the edge of the gas disk, and there was no sign of it diminishing whatsoever. So that raised the question, well, how big is this dark matter halo? How far does it actually go? So they decided to have a look at the orbital speeds of two satellite galaxies to our own, the small and large Magellanic Clouds. So these are two irregular dwarf galaxies orbiting our own galaxy. And they found that the dark matter extends at least as far as these satellite galaxies. It may well extend far beyond them. It might be the case that these dark matter halos extend half the way to the next galaxy. So these dark matter halos are absolutely huge. They're enormous. So what we've hopefully learned so far is that we've discovered that normal matter dominates the solar system. We really don't need to bother with dark matter when we deal with traveling to the moon or the outer solar system. That we can determine the total mass within a body's orbit, but just by knowing its orbital speed. By looking at the star orbits in Andromeda, we showed that not only that dark matter was needed, but what the distribution of dark matter was within the galaxy. That spiral galaxies are surrounded by enormous dark matter halos, and that our dark matter halo extends at least as far as the Magellanic Clouds. And it also becomes apparent that dark matter dominates in the halo, but not in the galaxy's disk. So what we think is that the dark matter is very evenly spread. Its highest density is at the center of the galaxy, and then as you go out into the halo, it's perfectly symmetrical or very symmetrical, but its density ends up reducing. But the average density of the dark matter is way below the density of normal matter in the disk. So the only reason that dark matter dominates the total mass is because the galaxy's disk is a very small volume compared to the dark matter halo sphere around the whole galaxy. So dark matter is really quite sparse, but there's so much of it, there's so much volume that it occupies that it ends up contributing to 85% of the total mass. And that's why we're not seeing it in the solar system. It might well be there, but because its density is so much lower than ordinary matter's density, it's negligible in comparison. So we know that we have dark matter halos around spiral galaxies, but what about elliptical galaxies? So this is a heavily overexposed image of an elliptical galaxy. And elliptical galaxies, we think they're formed when two spiral galaxies end up colliding and merging. And it ends up randomizing all of the star orbits. So instead of having a stellar disk, we have stars orbiting in a chaotic manner with no preferred direction. So they end up as either spheres or rugby ball type shapes, hence the elliptical name. And that makes it quite difficult to study their orbits to determine the mass and the amount of dark matter. We can end up determining their mass by something called the Varial Theorem, by looking at the average speed of stars within the elliptical galaxy. But to determine whether a halo exists or not, we need to look at stars that are orbiting the elliptical galaxy, but further away. And because of their chaotic orbits, the absorption lines in stars just don't stand out well enough, and you just can't make an accurate measurement. So they came up with a really bright idea. They decided instead of using stars, they would use the emission line spectra from planetary nebula instead. So all stars like the Sun will end up at the end of their lives becoming a red giant, and then eventually they'll shed their outer layers, leaving the star's core naked at the center, which we refer to as a white dwarf. And the outer layers then end up getting illuminated by the ultraviolet light from that naked core, which makes it light up with emission lines. And those emission lines, they're very pronounced. So, and there's not that many of them, so it's not a confusing picture. And hence we can end up measuring the orbital speeds around the elliptical galaxies and determine that yes, most of them do indeed have a dark matter halo. Some of the results that came back show that some elliptical galaxies, the orbital data didn't give any evidence for dark matter halos. It might be that that doesn't exist in those galaxies, but more likely we were just unlucky where these stars were in their orbits. Because the orbits are quite chaotic in elliptical galaxies, these orbits might have been highly elliptical, and we might have caught the stars when they were right near the end of their orbit, and hence traveling very, very slowly. So it may be that all elliptical galaxies have dark matter halos, but we definitely know that most definitely do. So now we rewind a bit to the evidence that our heroine had ended up using to figure out that measuring orbital speeds would be a good idea. And that's Fritz Zwicky back in 1933. He was studying the Coma galaxy cluster, and he was measuring the speeds of the galaxies at the edge of the cluster. He discovered that they were traveling too fast for the observed mass of the cluster. So he was one of the first to end up hypothesizing that there must be some form of invisible material inside galaxy clusters that was making the galaxies move much faster than they should be. For some reason, his colleagues tended to view him as being slightly crazy. So they really didn't take what he said particularly seriously. What his measurements showed was there must be 400 times more mass within the cluster than we actually observed. Admittedly, his estimate was more than an order of magnitude out, but nonetheless, he had found the right explanation for it, even if his measurements were wildly wrong. And indeed, today, with more accurate measurements, we know that there is dark matter spread evenly inside these galaxy clusters, and yes, it does make up about 85% of the cluster mass. A great cartoon. So, as the cartoon says, an obvious explanation might be that, well, perhaps gravity works differently at very large scales. We've tested gravity really, really well in small scale systems like the solar system. But what if it works differently at vast distances? What we would need is for gravity to be stronger at big distances than our theories currently predict. Great idea, but it really doesn't fit the data as the cartoon comments. We find that with different sized galaxies, some will fit it, others won't. So if you're going to explain it by modifying gravity, you really need a more complex theory. It can't be a straightforward, just depending on big distances. So here we come to MOND, the Modified Newtonian Dynamics. I promise you I will not be going through the mathematics. There won't be a test at the end, but I thought I'd put the slide up just so you could enjoy the squiggles. So what modified Newtonian dynamics ended up suggesting was, instead of gravity being modified by big distances, instead it ends up being modified when the gravitational field gets very, very low strength. So they're saying that when the gravitational field is very, very, very weak, it ends up weakening with distance more slowly than we would expect. And that would give the extra strong, the gravitational field then, at big distances from the galaxy center. Those gravitational fields are really quite weak, and they'd be weak enough for this change to the theory to kick in. And then, although they are still very, very weak, they would be stronger than we would have expected. And by doing that, in the vast majority of the situations, you can explain away dark matter. It can fit the data surprisingly well. All you need to do is choose the right value for this new constant they've introduced, A0. And interestingly, they have to modify the Newton's law of inertia as well, the F equals ma, because if they didn't, giant stars would end up orbiting at different speeds to small stars at the same distance. And clearly we don't observe that. So they have to modify both gravity and inertia. So despite its big successes, and for a while it was taken quite seriously, it had several problems. One was that it didn't comply with special relativity, although later on, fairly recently, a modified version was created called tensor vector scalar gravity, which does comply with relativity, but it's really not as neat as general relativity. But it kind of works. But there are bigger problems as well. It doesn't work for galaxy clusters, and it also doesn't work for some of the small low luminosity galaxies that we're now finding, which have a particularly large amount of dark matter in them. So most scientists have ended up rejecting MOND. Only a few are still soldiering on, saying that, well, we've got something wrong, but it's we'll get there in the end. Yeah, most scientists just feel it doesn't fit all the data we've now collected. So we now need to move on to the gravitational lensing, which I attempted to demonstrate at the start of the talk. We can see that if we imagine the space-time continuum as a rubber sheet, we can see that large masses on that sheet will end up distorting it, and that gives us a very intuitive idea as to why curving the space-time continuum can affect how a mass travels. So if we roll a ball bearing across this rubber sheet, we would expect it to be its path to be deformed by the dip. It's important not to take the analogy too far. In reality, it's a great deal more complicated what's occurring, and it depends a great deal more on the time dimension than the spatial dimensions. But the intuitive picture is useful, and we can see that it's not only bending the path of normal objects, it can also bend the the path of light as well, hence producing these gravitational lensing events. And the important thing to realize is that the galaxy that causes the lensing, either the galaxy or galaxy cluster, is in the middle, and the galaxy that's going to be lensed is much more distant. And we need a very good alignment of that galaxy through near the center of the lens on its way to the Earth. And if those conditions are met, then we'll start seeing distorted arcs, or if we get a very close alignment, a full circle. So here's an example of a galaxy that had an almost perfect alignment with a closer red elliptical, and we're getting a horseshoe, almost a full circle. In this case, we're not lensing an incredibly distant remote galaxy, and that's why the lens galaxy is blue rather than red. It's a spiral galaxy. It's perhaps 2 or 3 times further away than the elliptical galaxy that's causing the lensing, and it's giving you this beautiful demonstration. And we can use this gravitational lensing to determine where the mass in the lensing object actually is. Now this false color image is of the bullet cluster, which is a galaxy cluster. In fact, it's 2 galaxy clusters that have collided and traveled through each other. So what we have is we've got the visible image is showing a cluster of galaxies on the left here and a cluster of galaxies on the right, and they've both ended up traveling through each other, and they've now come out the other side. And galaxy clusters, there's a lot of space between the galaxies, so typically you won't get any head-on collisions, and the galaxies will just go straight through without any real trouble. It's just their motion will be slowed down a bit due to the gravitational attraction, but otherwise they'll be pretty much unaffected. But the galaxy clusters also contain a great deal of gas, and gas is sticky stuff. So when the gas ends up colliding, you get interactions via the electromagnetic force, which means the gas ends up colliding heavily, and its motion will be dramatically affected by the collision. And we can see that the 2 gas clouds have gone through each other, but their motion is significantly diminished. So they're now the gas is mostly in the space between the 2 galaxies. Now, the gas in galaxy clusters, there's about 10 times more mass in the gas than there is in the stars, in the actual galaxies themselves. So when we do the gravitational lensing, if dark matter doesn't exist, we should find all the lensing concentrated on the gas and not the galaxies. But that's not what we find. We find that the blue area, so the red area indicates the gas, and that's from the X-rays due to the shock fronts as the gas collided. The blue region is from where the mass is from the gravitational lensing, and we can see that the blue is well away from the normal mass distribution of the gas. It's where the galaxies are, and this is exactly what we'd expect if dark matter is making up 85% of the mass of the system. Because just like the galaxies, the dark matter doesn't collide with itself, it doesn't collide with the galaxies, it doesn't collide with the gas, so it will just go straight through, and it will only slow down a bit due to the gravitational pull. So it will behave in exactly the same way as the galaxies, and that's exactly what we've ended up seeing in the bullet cluster. And this image was, many felt, was the last nail in the coffin for the modified gravity theory, because it's just so difficult to explain this happening with MOND. So if we can't solve the problem by modifying gravity, then we need to determine what sort of stuff ends up actually making up dark matter. This image is an artist's impression of a brown dwarf. And that's the type of object that the Macho explanation of dark matter ends up requiring. So Macho stands for Massive Astrophysical Compact Halo Objects. So the idea is, if we have enough things made of normal matter, which are just too faint for us to currently observe, maybe that could just explain dark matter. And brown dwarfs, for instance, unless they're very close to the Earth, they tend to be too dim to see. We can also have black holes and faded white dwarfs, planets. So it was initially a very popular theory. So they set about trying to test whether these objects are really out there or not. Of course, that's a bit tricky if they're too faint for you to see. But they came up with a very cunning plan. They decided to use something referred to as microlensing. So in microlensing, you have a background star, a very distant background star, and something that you can't see, like a brown dwarf or a planet, that comes exactly in line with that in between the Earth and the distant star. And when you get that, the background star's brightness ends up getting much, much brighter. This is a microlensing. This is a real microlensing event. You don't get the distorted arcs that you get with galaxies because the distances involved are just too small. The lens just isn't big enough to do that, but it is big enough to brighten up the star. Of course, you don't expect many micro lensing events to happen because you need such precise alignment. So 3 different groups ended up looking at 3 different targets. And what they needed was a background star field that was extremely dense and would hence make the lensing events more frequent. So one group chose the Large Magellanic Cloud, another group chose the Small Magellanic Cloud, and a third group chose the nucleus of our galaxy. And they set up their observing program, and they did indeed find these lensing events. In fact, one group was particularly successful at finding them, but their success was actually largely because they had a lot more false positives than the other groups. One of the major problems they have is what's referred to as self-lensing events. A rather confusing name, given that a self-lensing event is where you've got a foreground star which is exactly in line with a background star. So you're getting a true microlensing event, but it's from an ordinary star, not from a brown dwarf or a planet or a black hole. You can also occasionally get variable stars that look like a microlensing event. So those need to be weeded out as well. So microlensing doesn't give you an exact amount of dark matter, but what it can do is give you an upper limit. You can determine, well, given the number of stars that I'm observing in the background, I know how much, what area around that star would cause a microlensing event. If I find n events, I can scale that up to knowing how many brown dwarfs are actually out there. And they found that the upper limit was 20% of the required dark matter. So we know that dark matter could be anything from a negligible amount of Macho objects to 20% of it. Most astronomers would probably go more towards the negligible amount, just because it's very difficult to explain why you'd get so many of these objects in the galaxy's halo. Failed stars or old stars, they should all form in the galaxy's disk. So how did they end up getting up into the galaxy's halo? And we have no valid explanation as to how that could have happened. So the vast majority of astronomers feel that Machos really just aren't a valid explanation. So it's now very out of fashion. So I think I'll skip this summary slide, and we'll carry on. So we now move on to our final explanation for dark matter, WIMPs. And that stands for weakly interacting massive particles. So this theory is suggesting that it's an undiscovered elementary particle that's causing dark matter. These particles must be perfectly transparent, so that they don't interact with light at all, and they must almost never interact with ordinary matter as well, and hence they can be invisible, and then they would fit the bill. So in order to understand a bit more about what these yet to be discovered particles, what sort of behavior they would end up having, I first thought we'd give a very quick introduction to the four fundamental forces of nature. So we have the strong force, which is the strongest force of all, and its job is to keep the nucleus together. It binds the protons and neutrons at the center of an atom together. It's a very short range force. It only has effect about over roughly atom nucleus sort of sizes, but it's very, very strong. The next in strength order is the electromagnetic force. So the electric force and magnetism have been combined from a model point of view into a single force. And this one is like gravity. It's an infinite force. It will, there's no distance, and it's still very, very strong. We then have the weak nuclear force, which is really very weak and very short-ranged. It is active over the width of a neutron or proton, and its main job is to deal with nuclear decay, things like a neutron decaying into a proton, electron, and a neutrino. And then the fourth force is gravity, which is ultra weak. We know you can know that it's very, very weak, given that the whole of the Earth is trying to pull you through the chair you're sitting on. The whole of the Earth, yet the electromagnetic force in the chair is equally counterbalancing that with great ease. So gravity is a very, very weak force. So now we've had an overview of the fundamental forces. Let's have a look at what we actually require. So here's my image of an atom. And we'll first start with the electrons and protons. We'll look at the familiar matter and see why they won't fit the bill, why they're not good candidates for dark matter. And as we see what the problems are, we can then move on to a clearer understanding of the undiscovered particles, what sort of properties it needs to have. So we'll start with the proton and the electron, and straight away we know they're completely unsuitable. They're charged particles, so they know all about the electromagnetic force, and that means they interact strongly with light. They can emit, they can absorb, they can scatter, so dark matter definitely isn't charged. They're definitely not like protons or electrons. The neutron, on the other hand, is far more plausible. It has no charge, so it's going to be completely invisible to light. It's not going to absorb, it's not going to emit, it's not going to block, it's going to be completely transparent. So the neutron initially looks very plausible, but it has a couple of problems. One is that it's unstable. If you take it outside the atom, it decays fairly quickly into a proton, electron, and neutrino. So we would need a stable version of a neutron. But it's got another problem, and that's that it knows all about the nuclear strong force. So for example, if we fire a neutron at a uranium atom, the neutron will interact with it very strongly indeed. And indeed, in the right circumstances, that can cause a nuclear explosion. So clearly, our dark matter particle has to not have anything to do with the nuclear strong force. So the question is, do we know any particles that actually fit the bill? And the surprising answer is, yes, we do. Right back in 1970, a very good candidate for dark matter was discovered, the neutrino. It's an almost massless particle that travels almost at the speed of light. It has no charge, so it will be invisible. It won't interact with light at all. It won't emit. It won't absorb. So that's great. It doesn't interact with the strong force at all. So that's perfect. It interacts with the weak force, but that's okay because the weak force interacts with matter so rarely that it won't make much difference. And it does have a tiny amount of mass. So maybe the neutrino could explain dark matter. And we have a lot of them because stars create neutrinos in vast quantities. So for example, where you're sitting on the Earth, the neutrino flux from the sun, there'll be 65 billion neutrinos per second that are traveling through your fingernail at the moment. And even at night, where the neutrinos have to go all the way through the Earth first, there are still 65 billion neutrinos going through your fingernail. So that they're there in vast numbers. They're made in even bigger numbers in supernova explosions. And they were made in vast numbers during the Big Bang as well. So it all looks quite promising. Unfortunately, again, there are a couple of snags. The first is that although they're there in vast numbers, their mass is just too small to account for the vast amount of dark matter. So they can only make up a small percentage of it. And the other problem is that they travel too fast. They're what's described as hot dark matter. So physicists, their idea of cold or hot when they're talking about particles is the speed that the particle travels at. So a cold dark matter particle is one that travels slowly, whereas a hot dark matter particle is one that travels near the speed of light. And that's important because in order to get dark matter to clump together into a halo, we need the mass of the halo to be high enough such that the escape velocity from that clump is higher than the speed of the particles. So if you've got a particle that travels at almost the speed of light, you need an enormously large clump of dark matter in order to trap it. So we would end up with absolutely huge structures. And that's not what we see. We see dark matter halos that are much smaller than that and just wouldn't be able to have that massive escape velocity. So we know that dark matter can't be made up of hot dark matter. It either needs to be warm or cold. I'll stay with that slide for a bit longer. So physics now, we now need to turn to particle physicists and ask them for a bit of a hand to consult their theoretical models to see, well, we need a particle we haven't discovered yet, but have you got any predictions for particles that fit the bill? And particle physicists, they have what's referred to as the standard model of particles. And that's been a really successful theory. They've managed to predict lots of things from their standard model. And when they've gone to look, it's been confirmed very accurately. But the standard model has some gaps in it. So they've ended up coming up with a new theory to plug those gaps called supersymmetry. And that invents lots of extra particles. And it's a really neat theory. It ends up explaining lots of difficult, tricky things. So it's very popular. It also makes string theory possible. Without it, string theory isn't really viable. And best of all, it ends up predicting a particle that's absolutely perfect for dark matter. So perfect, they refer to this as the WIMP miracle, because we need this dark matter particle, and our best new theory of particle physics is predicting it. So this is absolutely brilliant. Unfortunately, now that the Large Hadron Collider has been upgraded to use much higher energies, it's been looking for the particles that the supersymmetry has been predicting, and it's failed to find them, which is a bit of a blow. And if it doesn't find them soon, it would tend to mean that the supersymmetry theory is wrong. And with it, its prediction of the particle for dark matter will go with it. So that's one big blow. The other blow is that we've now been searching for these predicted dark matter particles in these huge detectors built far under the Earth's surface. And so far, despite getting bigger and bigger and more sensitive detectors, we've still detected absolutely nothing. So that's again another big blow. So there are a few possible explanations as to why they've hit these significant failures. One is that if supersymmetry is wrong, then the dark matter particle might not be the one they've predicted. Maybe it's a particle that doesn't know about the weak force. And if the only force that it interacts with is gravity, then our detectors will be blind to it. They rely on a reaction with the weak force in order to detect the dark matter. So maybe we will never detect them through these detectors. Alternatively, maybe dark matter does still interact by the weak force, so we can still potentially detect it, but maybe there are none where the solar system is. Now, that might come about because we believe our galaxy was formed by lots of smaller galaxies colliding and being absorbed. So small galaxies gradually built up into bigger galaxies. So you get a situation where you might find the dark matter halos from the original galaxies end up staying together and end up orbiting the bigger galaxy. So dark matter might be clumpy within our own galaxy. And if it is, it's quite likely that our solar system is in a void where there are no clumps. And if that's the case, then we might be looking for exactly the right particles with exactly the right equipment, but maybe very few are going through our equipment. So certainly plenty of problems for them there. They're also looking for dark matter in other ways as well. So one possibility is they think that the dark matter particle might be its own antimatter. And if that was the case, when two dark matter particles came together, they would annihilate each other and end up emitting gamma rays. So they've been searching for gamma rays to try and find dark matter that way instead. But it's tricky because you've got to try and differentiate between a dark matter annihilation event and normal events which might produce gamma rays. So there are still no confirmed dark matter detections from the gamma rays either. And my final slide is of the cosmic wave microwave background radiation, the cosmic microwave background radiation. Now, the reason that this is important is it gives a completely independent way of calculating how much dark matter the universe has. What the cosmologists can do, they can look at this background radiation left over from the Big Bang. And the blue regions are areas of very, very slightly lower temperature than the red regions. And they can end up looking at the pattern how rapidly it changes from hot to cold. And by plotting graphs of this, they can end up predicting how much dark matter was needed when the universe was first forming. And amazingly, their calculations are completely consistent with our other completely independent measurements of dark matter. So this is a very big support of the idea that dark matter really is real and it's needed. The other thing is that when we run computer simulations of how the universe formed, it doesn't work if we don't include dark matter. The reason for that is that when the universe, when the Big Bang first happened, when initially the material that was created was all ionized, and that made it opaque. So light couldn't escape. And instead, it was interacting very heavily with the matter. It was tightly coupled to it. And that stopped the matter from contracting. It kept it very evenly spread. It couldn't start collapsing and forming galaxies. But dark matter wasn't coupled to the light at all. So any of the tiniest density variations, dark matter could start accumulating in those areas and hence building up those dark matter halos. So later on, when the universe ended up becoming transparent again, when the coupling finished, the matter could then fall into these gravitational wells created by the dark matter, and hence speed up the creation of galaxies, which might not have formed at all if it hadn't been for the dark matter. And indeed, the speed of the dark matter particle determines how big these dark matter wells are and determines the size of those initial galaxies. And the predictions for the that we have end up explaining the universe that we observe really quite closely. Yeah, and I think I'm pretty much out of time now, so I will leave it there on this summary slide and invite questions.
Excellent, John. Thank you. All right. Well, I don't think we really need to worry about doing the chat room. So if anyone has a question, you should be able to unmute yourself and just ask away.
Hello, John. It's John Barry Smith. Have
Hi.
you got an average density for dark matter that's around us? How many kilograms per cubic meter? Or micrograms per cubic?
I don't. I guess it could be worked out, but I've not actually seen that. I guess what you'd need to do is determine the volume, the approximate volume of the galaxy's disk, and then the volume of the sphere that the dark matter's that corresponds to the size of the disk. And it would be the crucial thing would be how thick that disk is, and of course the densest material is at the central plane, and the density decreases exponentially as you move away from the plane. So it's not a trivial calculation, but I'm sure it's been done. So no, I don't know what it is, but what I do know is it's certainly very, very low compared to ordinary matter. And that's why we just see no evidence of it in the solar system. But of course, when you're talking about 3D, a sphere has so much more volume than a thin slice through the center. So that's why we can end up with a 85%, 15% ratio. So sorry, no, I don't have the figures for that.
John,
Okay. Yep.
Fantastic talk in there. Is there any evidence, if it's a halo around galaxies, is there any evidence whether it's attracted to the galaxy or is emitted from inside the galaxy?
Right. The halos are stable, so that means they would either have to be emitted at a continual rate, or they're particles or bodies that are gravitationally bound to the system. And since we have no mechanism for creating and emitting this matter, then I think it has to be gravitationally bound material. And we don't believe it's material traveling from one halo to the next. We do think it's gravitationally bound to a single halo. Does that answer the question?
Oh, thank you. Yes, as much as my mind can absorb.
John, I've seen there's been recent data indicating that warm dark matter rather than hot dark matter and cold dark matter could account for the Hubble papers that were produced. What's your thoughts on warm dark matter?
Well, that's a really good question, an excellent question. Initially, they were going for cold dark matter because that's what supersymmetry was predicting. So because we had this brilliant prediction, and because we then knew exactly how to build our detectors to give us our maximum chance of detecting it if we arranged it around this prediction, that's what everyone went for. But the evidence would tend to point for warm dark matter instead. And the reason for that is due to the dwarf galaxy problem. There just aren't enough dwarf galaxies. If we have cold dark matter, then the minimum size of these dark matter halos is much smaller, and would expect a large number of these small lumps to gradually have formed the bigger galaxies. But the mathematical models end up predicting that we should have a lot of these dark matter clumps left over. Maybe there's lots out there that we can't see because they don't have many stars and they're just a dark matter galaxy. But it seems perhaps more likely that dark matter is warmer, and hence the smallest size lump was bigger, and that would explain our lack of all these dwarf galaxies we would have expected. So now that we're not constrained to cold dark matter because supersymmetry looks as if it is probably going to turn out to be wrong, then I think warm dark matter is much more likely than cold. We know it can't be hot because then galaxies would have to have formed as big galaxies and then broken up to become smaller ones. And that's not what we observe. When we look to the edge of the universe, we see small galaxies, and as we come closer to our own time, they build up to be bigger. So we know hot dark matter's off the agenda. So it's between cold and warm. And yes, I think warm is a much better bet.
Thank you.
John, another question.
Okay.
I presume because dark matter interacts gravitationally, what happens when it gets sucked into a black hole? Does it get hot like ordinary matter gets hot as it's sucked into a black hole?
Ah, good question.
Or does it just disappear?
Right, okay. So no, I don't think it would get hot because it doesn't interact with anything around it. Mm-hmm. So gas tends to get hot because it's ending up interacting with the particles around it, and by doing that, it's transferring gravitational energy into heat energy. But with dark matter, it's a lot different. It's more like stars and black holes than it is like gas and black holes. So, for instance, if you have loads of stars around a black hole, the intuitive idea is, well, the black hole will just gobble up all those stars. They'll fall into the black hole. But that's not what happens. Instead, they end up orbiting the black hole. And those orbits are completely stable. They will orbit it forever. You would need a star traveling directly towards the black hole in order for the black hole to be able to swallow it. And that very, very rarely happens. So with the
yeah, go ahead.
with the dark matter particles, unless they're going directly towards the black hole, if they're slightly to one side, they'll just speed up to be very fast as they approach it, and then they'll orbit it. They'll end up going out the other side and end up in maybe in a highly elliptical orbit. And only those that get within the event horizon would end up being caught by the black hole. So you'd expect that to happen occasionally, but most of the dark matter particles would just zap past it. And because you've got no, all the energy is being transferred to the speed of the dark matter particle. So it's not going to get hot, it's just going to get faster. Of course, physicists often refer to fast particles as hot anyway, but it's a bit different from temperature.
Right. So they might exceed the speed of light?
No, they would have to be limited by the speed of light. So if they came within the event horizon of the black hole, they would be caught by the black hole. And then after that, of course, physics breaks down. We don't really know what happens. So yes, the black hole is capable of capturing them, but only if their initial path takes them into that event horizon. Otherwise, just like stars, they will have orbits around them. So we have a supermassive black hole at the center of our galaxy, but the stars close by, they're in stable orbits. They don't suddenly get eaten.
John, follow-on
Yeah.
question to a very good presentation, thank you. In the case of you referring, or everybody referring to cold, warm and hot dark matter, what sort of temperatures are they referring to?
They're not. For a temperature to be well defined, you need interaction between the particles. So for a gas, you need a certain distribution of speeds within that gas that occurs quite naturally due to the collisions. And from the shape of that velocity curve, you can define a temperature.
Yeah.
But with particles that don't interact, there's no such thing as a temperature.
So in that context, you're talking about speed, in which case,
yes.
What sort of speeds are you talking about?
So for hot dark matter, we're talking about close to the speed of light.
Right, so truly relativistic.
Yes. Though I think the definition for cold and warm is rather fuzzy. I'm not aware of any particular
so fuzzy logic kicks in.
Yes.
Okay.
So I might be wrong, but I don't
know
know of any strict definitions.
Okay, so there's no so many meters per second or megameters per second or whatever. No,
I guess a more relevant criteria would be what size, what the minimum size dark matter halo that could form would be. And of course that depends on the mass of the particle and its speed. And that really is the critical quantity.
So it's a lovely Hertzsprung diagram that can't be defined.
Yes, indeed.
Okay, yeah, top, thanks.
John, yeah, I've got a question. John,
okay.
The question on this, if they were their own anti-particle, and if they collided, they would release energy. Now, I thought this was supposed to be, was gamma ray or something like that. It was
That's right, yes, gamma ray.
So what mechanism would that be, since a gamma ray is electromagnetic force, and yet these particles don't interact with the electromagnetic
How interesting. That's not something I'd ever contemplated before. Yeah, so you're certainly correct that if the gamma rays were emitted because it was emitted from the particles themselves, it would be impossible because they don't have charge, they don't experience the electromagnetic force. It could not happen. So it has to be a two-stage process. So during the annihilation, the particles are destroyed completely and they're converted entirely to energy. Once they're pure energy, that energy has to become something, but the particles no longer exist. They're no longer relevant. All we have is that energy. And I haven't read up on the physics of this area yet, but I assume that gamma rays, if the energy is in the right level, if it's high enough energy, package of energy, then gamma rays are the most common thing for it to become. I suspect it could probably become many things, but gamma rays are just the more likely of that scenario.
I just wonder if it could do it via the weak force.
I don't think so. I think it has to be something that, I think it has to be that two-stage process where it needs to become energy first, because the particles themselves are not capable of emitting gamma rays. But any matter, when it self-destructs, doesn't matter what type of particle it is, it will end up producing typically electromagnetic radiation when it gets annihilated. But yeah, interesting. I'd not considered that before at all.
John, Dave again. Where you've got their WIMPs predicted by supersymmetry, and obviously fully understanding what you related to the shaky ground it's put supersymmetry on, is that the same supersymmetry that is being referred to where two photons, or I think it's photons, if you do something to one, or sorry, no, it's electrons, isn't it? If you do something to one, its supersymmetry partner will respond in the same way regardless of distance, as in the sort of whole concept of greater than light speed communication, if you will, although that's probably the wrong terminology to be using. Does that mean that that concept, if it is the same concept, is also being brought into question?
No, they're two completely different.
They are different.
Areas.
They're just given the same name.
So one of them, I think it's more commonly known as quantum entanglement.
Yeah.
Oh, is that what it is? Sorry,
Yeah.
that's my mistake.
Yeah.
Then I'm just putting the wrong badge on it.
That's very strange, very spooky.
Yeah,
completely different.
Yeah, straight out of Star Trek, really, isn't it?
And that's very much quantum mechanics rather than particle physics as well.
Yeah.
Which intriguingly, those two tend to be very different fields of research. Even though particle physics must depend on quantum mechanics.
Well, exactly. So that you're going to end up with solving the electromagnetic forces, etc., with gravity and sorting that one out eventually, but then still end up with this this alternate two pairs or a pair of entities that won't work together.
Yeah. So supersymmetry, I don't know that much about it, but it's inventing a whole set of new particles, so we get double the number of particles in a sort of symmetrical arrangement. I think that's where the supersymmetry comes in on the name.
Doesn't that sound just like multi-dimensionals?
Maybe that's why it fits in so nicely with string theory. And I always have a problem with highly mathematical theories that have no evidence behind them.
Yeah,
because
most untestable.
They're it's so easy to fit the maths to a particular solution, as Mond did, the modified gravity. If you have the data already that you're trying to explain, you can usually come up with some clever maths to fit it.
Ooh, yes.
And you've got so many possibilities, but there's only one answer. And it seems to me that humans are very bad at guessing the right mathematics. They usually get it wrong. So I'm never that surprised if one of these purely mathematical theories ends up needing to be modified.
Well, that comes down to the simplest one of all, is although flicking a coin is a 50-50 chance, most people will get it wrong. You've got to give them a lot of goes at it for it to actually balance out.
Yes, yes, indeed.
So it's probably comes out of that same camp. Thanks.
Okay.
All right. Anybody else? All right. Well, thank you, John. That was quite enlightening, and yeah, very good. Let's give a nice round of applause to John. Thank you.
Ooh, cheers. Thank you.
Yes.
We're still waiting on your virtual dome crawl now, John. You're not getting out of it.
No, I know. Yeah, I gotta. I gave you two choices, and John's like, Dark matter. I'm like, all right, dark matter it is. So.
But you realise the protagonist in all this is sitting pretty because he doesn't have a dome at the moment, but woe betide the day he does.
Yes. And of course, Mill Dave is fairly safe because he's already done his. So.
Been there, done that. It's like the converted smoker, isn't it?
Indeed.